Okay, repeated eigenvalues. So what we'll do is we'll look at the general solution and two examples. So repeated eigenvalues, we're going to handle these very differently from previous cases. Usually we've seen that repeated eigenvalues means multiplied by t. So we'll look at this thing and say, if this is a solution, what has to be true about this? Well, being a solution means that this has to be true. Differentiate that. If I differentiate this, I'll just get a lambda e to lambda t times the vector w1 plus e to lambda t w2, because that's just differentiating the t there, plus lambda t e to lambda t w2, because when I differentiate the e to lambda t, I pull down a w, equals m times this. So m times e to the lambda t w1 plus t e to the lambda t w2. So if I group things by e to lambda t, I get e to the lambda t lambda w1 plus w2, that's these two terms, plus t e to the lambda t times lambda w2 equals, well, e to the lambda t is a number. It varies depending on t, but no matter what t you pick, if you plug it in, e to the lambda t is just a number. So I get e to the lambda t times mw1 plus t e to the lambda t times mw2. So since these have to be equal to each other and this function are different, that means I get two equations by matching the coefficients. So if I match the coefficients on e lambda t, I get lambda 1 plus w2 equals mw1. That's this is equal to that. If I match the coefficients on t e to lambda t, I get lambda w2 equals mw2. This has the nice fact that w2 is an eigenvector, because that's what it means to be an eigenvector. That's the eigenvector equation. It becomes important for graphing, but not so much for the solution. This gives you a way to solve for w2. w2 equals mw1 minus lambda w1. And we want to make a note here. What is y at 0? So if I take this equation, I plug in t equals 0, what do I get? I get e to the 0 times w1, but e to the 0 is just 1, plus 0, right? If we plug in t equals 0 there, times 1 times w2. So the initial condition is just w1. So what do we get here? If we know the initial condition, we get w1. And if we know the initial condition, we can just do this multiplication, get w2, and for free, we get the fact that w2 is an eigenvector. So that's the upshot of how to solve these kinds of things. It's nice because there's no k1 and k2 because we built the initial condition right into the solution. So what's the solution for this initial value problem? Well, first off, we need to find the eigenvalues. And we take, determinant of -3 minus lambda minus 1. Down here, we'll have 1 minus lambda and 4 equal to 0, right? And then solve for lambda. Multiplying all this out, you get what? -3 minus lambda times 1 minus lambda plus 4 equals 0. Another semicolon. If we multiply this out, maybe just do an arrow. Lambda squared, I get a minus lambda plus 3 lambda, so a plus 2 lambda, and then a -3 plus 4, and that's a lambda, not just two random lines. And we end up with lambda squared plus 2 lambda plus 1 equals 0, and we can factor that. So we have a repeated eigenvalue. Repeated means that we have two factors here, right? It's lambda plus 1 times lambda plus 1, but they both have the same root. Okay, so you can write down the solution pretty easily. Y of t equals e to the minus t w1 plus t e to the minus t w2. w1 is our initial condition, which is 3 minus 1. And w2 equals m times w1, which is 3 minus 1, minus lambda times w1, but lambda is minus lambda times w1, except lambda is -1, so it's going to be plus 3 minus 1. And our matrix of coefficients is -3, 4, -1, 1. Times our initial condition plus the initial condition. And that gives W2 equal to, well, -9, -4 is -13, plus 3 is -10, -3 minus another 3 is -4, minus another 1 is -5. So there's our solution. E to the minus t plus t e to the minus t times -10 minus 5. And we note that this is an eigenvector. So what does a solution curve look like? What I'll do is I'll pull down my solution here. Y equals e to the minus t times 3 minus 1 plus t e to the minus t times -10 minus 5. Okay, so what does our solution curve look like? What does that look like? Well, let's note that actually, I want to go up here to note this. Note something about this process is if my initial condition is an eigenvector, then W2 equals 0. Right? Because that's what it means for an eigenvector, is that m times an eigenvector equals lambda times an eigenvector. So what does that tell me about this? If I take an eigenvector for W1, then this is the solution, and this will just be 0. So the eigenvector times the eigenvalue raised to the lambda is always a solution. And so that means when we're trying to graph this, that's a solution. So is 0, 0, of course. So -10, -5. Let's see if we go out 10 units to the left, halfway on the. So this is a solution. And we're going in because it's e to the negative t. And of course, if we multiply this by -1, fudge, sorry, that should be down here. I wonder if I can undo stuff. Yeah, I can do some undoing. Okay, -10 -5 is actually down here somewhere. So e to the minus t -10 -5, and that's going in. If I multiply this by -1, I get e to the minus t 10 5, and that's going in. So this is my two eigenvalue eigenvector solutions. We don't know we don't have another eigenvector, so we can't do another eigenvector solution. But what we can do is think about what happens as t goes to infinity. So this was starting at 3, 1, 2, 3, minus 1. That was my initial condition. I want to know, where does this thing go? Well, this is y equals e to the minus t times 3 minus 1 plus t times minus 10 minus 5. What happens as t goes to plus infinity? Well, this is driving everything to 0, but as t goes to minus infinity, what we're going to be doing as t goes to minus infinity is this term will dominate, and so we can ignore that one because this has got a t in it. And this is going to t goes to minus infinity. That means we're actually going to come in tangent to minus of this vector. So as t goes to minus infinity, and we started down here, we're going to come in tangent to this vector. As t goes to plus infinity, right? No, sorry. As t goes to plus infinity, this goes to 0. We come in tangent to this vector because we can sort of ignore that one. As t goes to minus infinity, this goes to infinity, so we're going out towards infinity. And again, as t gets bigger and bigger and bigger, this term dominates that one. So we should come in tangent to this, and we should go out parallel to that. We just need to know which way we're going. So again, if we look at the point 1, 0, at the point 1, 0, our vector field has minus 3, minus 1. So let's note here, we set x equal 1 and y equals 0, gives us x prime equals minus 3, y prime equals minus 1. So that's our vector at x equals 1, y equals 0. So at this point, we're pointing down that way. So what are my solution curves doing? They're coming in, and then they come in tangent like this, and they leave parallel to this thing there. So this initial condition could come in parallel to that and parallel to that. So tangent going in that way, parallel going in that way. And on the other side, we're doing the same thing. Right? We come in tangent to the eigenvector line, and we leave parallel to it. So that's what our solution looks like. It kind of is sort of like if you had 2 positive eigenvalues or 2 negative eigenvalues, that you come in tangent to one and parallel to the other, but here we only have one pair. So you are parallel to one side of it and then tangent on the other side as you come in. So it's a little bit of a swirl. It's a little bit of a real eigenvalues. It's sort of a borderline there. So, oh, this doesn't have an IVP. I should have changed that. So what does this look like? Okay, we need eigenvalues. And at this point, we can just read this off. What the equation will be, it'll be 4 minus lambda, because that 4, times 2 minus lambda, that 2, minus 1 times minus 1, because there's a 1 here and a minus 1 there. So we get lambda squared minus 6 lambda plus 8 plus 1, lambda squared minus 6 lambda plus 9, and we want that equal to 0. That's minus lambda minus 3 quantity squared equals 0. So lambda is 3 repeated twice. So our solution is y equals e to the 3t w1 plus t e to the 3t w2 where W1 equals initial conditions, W2 equals MW1 minus 3 W1 because lambda is equal to 3. But this is also an eigenvector, and we know that that eigenvector controls the behavior of this kind of thing. So since we don't have an initial condition, we can just solve this for a eigenvector. So we can just make up an initial condition, right? Set W1 equal to 1, 0. And then that means that M, which is 4, 1, minus 1, 2, times 1, 0, minus 3 times 1, 0, is an eigenvector. This isn't true in general, that you can do this, but it is in this particular case. So we get 4 minus 1, 4 times 1 plus 0, minus 1 times 1 plus 2 times 0, minus 3, 0. So our eigenvalue is 4 minus 3 is 1, minus 1 minus 1 is minus 1. Great. So what does our solution curves look like? Well, we've got a 1 minus 1 eigenvector solution here. That'll be e to the 3t times 1 minus 1. And it's going out because we have a positive exponent. And then we have it going the other way. E to the 3t 1 minus 1. Just multiply this one by minus 1 to get the opposite one. Those are eigenvector solutions. Along the way, we calculated this is the vector at x equals 1, y equals 0, right? Because that's what we plugged in here. So 4 minus 1, that means we're going to the right and down. So our solutions are coming out tangent here and ending up parallel there, tangent here and ending up parallel there. So knowing that this points to the right and down, that's telling me that all my solutions are going to cross the x-axis pointing to the right and down. And so I can say, well, they have to start here, go up here, and then approach the x-axis from the first quadrant and go down. And on the other side, they go the other way. And that gives us a graph of those solutions.